And welcome back. We are continuing to talk about cyclic Hamming codes, which are obtained by division. And I wanted to show you some MATLAB results and how to obtain coding and encoding matrices. We will speak of this more when we will work on our task 6 of the course project, which, let me show you, involved the simulation with coding and without coding, right? So this task. As for task 5, I will show you a general approach which you can use to check yourself, but you still need to show the entire division process in your course project, right? So you can use MATLAB here to check if you have calculated correctly the result, but you need to show the entire division process, how you have come to this result, right? So for that part, we can use data. I think it was help cycle generator of cyclic codes, right? Yes, I need package. You can use online Octave if you have problems with packages, but you still need to put this message into online as well, because you must load those packages there. Also, I'll see maybe, let's see, edit cycle again. Maybe or type cycle again. Maybe it's not a small. Yes, it's a dynamic linked function DLL file, meaning that most probably I will not be able to provide it you in such a simple way as for IWGN case, but I will show you the entire idea. Well, I'll describe and tell you how to generate those matrices by yourself. Well, only a bit later, right? So you can use the cyclic gen to generate the encoding and decoding matrices. So help cycle gen shows us that we can generate these matrices by this function, and we need to provide the code word length m and the generator polynomial and the type systematic or non-systematic. Let's see this in detail. So first is the decoding matrix. So let me name it a dec matrix. The first is encoding matrix, enc matrix, right? Cycle gen. The code word length for my case here is 7, right? From 1 to 7. So the first parameter is 7, and the generator polynomial is this one, Z3, Z1. That would be 1, 0, 1, 1. You must provide it in binary form here. And yes. So we have generated these two matrices. The only thing is that actually this MATLAB solution is not the best in the way that actually the control symbols are here located at the beginning. So basically that would be E1, E2, E3. It's still systematic, right? C1, C2, and C3 and C4. But you need to remember that when you are checking your calculations, that the actual result, first three symbols, will be in this case the control symbols. So let's make the code word for this example. For this example, right, when we have data block of 1101, let's specify this as some variable x, 1101, and perform encoding by multiplying x with encoding matrix, and not forgetting that we actually need to calculate modulus 2, because by default this calculation involves simple addition, like 1 plus 1 would be 2. Well, that's easy to show that we will get numbers 2 and 3 in this control, right? which is not what we want. So we put modulus. That would be our code word, right? And as I have said, here we have that information part, and here we have control part, which was here the same, only, well, this was here. But again, as you know, you can cyclically shift this code word 3 times in this direction and you would get that same result. So basically, I think that was help cycle shift, right? Help. Not this one. RRC. No, don't remember this specific command, but still there is a command which allows you to shift this. You can watch up on Google, maybe it. What I did, however, in my code was changed a little bit those two matrices. So basically, you can see for encoding matrix, we have here unity matrix, I matrix, diagonal matrix, and I have put that first. You can see it here. Then the remaining part was added after, right? So basically, I generated these matrices by this command and reorganized that matrix columns. Well, again, that's quite simple. Even more so that if we look the last column here, that is actually our generator polynomial, right? So generator polynomial has been specified as 1011. So this is generator polynomial. Only no, first number is at the bottom and the last number is at the top. Even more so, the second column is actually the same generator polynomial, but shifted, right? We need to shift that how many times? That's, well, wait a minute. We need to perform 2 shifts, right? 2 cyclic shifts to get this second column. And then we need an extra 2 shifts to get to this one. So basically, each column is a generator polynomial shifted by some number. Once again, I will in details describe you that later, but for now you can just use these matrices and make sure that you realize that, well, actually the control bits come here first in this solution, right? Similarly, I have rearranged the matrix for decoding device, right? Also, here is the diagram matrix, I matrix, which I have put at the end, since that's where my control symbols are. And here are the same generator polynomials, only it's shifted, right? So my generator polynomial was 1011. Here it's shifted. Well, actually, it's not exactly like that, but you can see here that generator polynomial, here that generator polynomial, and here, right? So I will explain that a little bit later, how these matrices are formed. But for now, as I have told, you can simply use this cycle gen or write them by hand from repeating this procedure. So if I use this code, right, and I have added the error in the first position, then we'll see the same code word. Now, because I have rearranged the code word also was rearranged, and the syndrome is 101 for the error in the first symbol, which is this case, right? So you can actually use MATLAB. Only the matrix is created more difficult way than for group code. But now let's go to the schematic diagrams. And first, let's start with encoding device. We'll see the logic, how it works in more details, but we'll skip these details for decoding dividing scheme, right? So we need some way to calculate that division, what we have been doing by hand. As you may know from computer architecture course, multiplication and division in processors is calculated by addition and shifting operations. So we'll need to implement that algorithm by using D-type flip-flops and XOR elements. So probably you understand that this means that we cannot calculate division fast. We will need certain amount of time to perform those shifts, right? More specifically, for encoding device, we will need K tacts because our information is represented by K symbols, for example, 1, 1, 0, 1. That's information of 4 symbols, and we will have to spend 4 tacts to get this information and perform division. For decoding device, we need to divide the entire code word, including the control symbols. That would be M tacts. So, in general, schematic look. In general, the shifting operation is performed by putting D-type flip-flops in series, one after another, right? Ignore for now these XOR elements. Consider that we are just making shift register from D-type flip-flops, right? And we make it cyclic. So that means that we connect the output of the last D-type flip-flop with the input of the first one. Now we have our generator polynomial specified here, so we are adding these XOR elements in those positions which we have in our generator polynomial. So for example, here we have G1 equal to 1, then we must put XOR here. For if we have G2 equal to 1, then the XOR after the second flip-flop also must be put, and so on, right? So that's the basic idea. We put those XOR elements in between flip-flops after the, for example, first, second, third, and so on, only if the corresponding coefficient of the generator polynomial is 1. Let's see a more precise example of the generator polynomial z3 plus z plus 1. So here we have z degree, and that's why we put XOR element after the first flip-flop. See, here is the first flip-flop, and we have in between XOR element. We don't have here z squared. That's why there is no XOR element here. So we connect directly to flip-flops. Also, this Z3 is present here, right? And the feedback network connects to the second inputs of those XOR. As you know, XOR has 2 inputs. The first input is connected to the output of the flip-flop trigger, and the second input is connected to feedback, which is also connected to the input of the first flip-flop. So if I would have the generator polynomial, for example, z3 plus z squared plus 1, actually, let me start TinyCAD and draw that in TinyCAD, since I recommended to use that for your course project schematics, so maybe we can draw it there. So we need the type flip-flop, right? No, not octal, dual type, this one. So place symbol, And our generator polynomial degree is 3. So that means we are going to need 3 such flip-flops in total. Also, we are going to need XOR elements. In this case, 2, because we have 2 XOR operations in this generator polynomial. So I'm going to put them here and then move around. So this is our first flip-flop, this is our second flip-flop, this is our third flip-flop. As I have said, we always have one XOR at the output of the last flip-flop, so we can safely connect them this way. Also, we have the power of 2, meaning that we must put that second flip-flop at the between the second and the third position. So basically, what we have this XOR element doing is calculating this sum, right? And this, however, calculates just 1, right? Which comes from the input. So let's connect the pins. And these are connected directly. Well, I'll not spend time onto moving around these, but you can actually move these numbers, right? 2 XOR here. Oh, already spent that time, all right? So you can do that. Then we are not going to use these outputs here as well as these inputs. And now we need the feedback. The feedback is connected to the input of the first flip-flop and to this XOR element second output, right? So this is the schematic for dividing data block with generator polynomial. This is not the entire encoder schematic, however, so let's see what's different. So for the entire schematic of the encoder, we need this switch, which will change its position, and an extra XOR element, which will add up our remainder. So this XOR is actually doing this operation. It adds to data with zeros our calculated remainder. And it does it after the 4th time interval, after the 4th tact. We'll see how this schematic works in details. So let's put an extra XOR element here. Also, we're going to need switch with 2 states. This one, right? Play symbol. We need also to rotate it a little bit. Okay. Let me just connect it because we must have here a node. And then by default, this switch is connecting this feedback, but at the same time moment, it will change, right? So for now, let it be like this, and our feedback, therefore, now is, well, actually connected to this point, right? While this point connects to this output. So by default, it's unconnected, right? So nothing comes here. and our input data is output at the end of this XOR without changing, because basically here we have 0 and anything plus 0 is that anything. And at the same time, we are feeding the very same data to our dividing schematic, right? So the complete encoding device for the generator polynomial z third plus z second plus 1, which is much more compact than for group code. I think you will believe me here that we have 3 D-type flip-flops, 2 or 3 XOR elements, 1 switch, and that's all. That's literally the same as, well, let's see, group code. No, sorry, that's the cyclic. And for the group code schematic, and compare that schematic with this one, we can obviously see that here we have much less elements. Well, maybe this and this, right? So it's indeed more compact and easy schematic. Even more so if we have M more than 7, like M31 and so on. Here you will have 31 output lines. Yes, you will need 4 these, I mean not 4, maybe even 8 of these registers. You will need a lot of these XOR elements, and somewhere around 7 input registers, right? Whereas for this schematic, you would need extra 2 flip-flops and up to maximally 2 more XOR elements. And that's all. That would be for M equal to 31. Much more compact. Also much more convoluted operation logic. If there, in this case, it was quite simple, we had equations and we just draw schematic according to those equations, then in this case the logic is much more convoluted and difficult. And I have prepared a special presentation showing how it operates. So let's see how the encoding is performed for the data block. So this is the very same diagram. Note that we have some synchronization signal, clock signal connected here also, but well, default position for this switch is number 2 here, and at the beginning of the operation we put zeros in these flip-flops, so we zero any output, right? That's the preparation phase. Next, we are sending some code word, some data. So our data is 1001. And what we need to do is to calculate the remainder, which must be this number, right? So we have calculated that in paper before to know what we should expect. And well, this schematic must calculate that remainder at the time moment for t. So we are start at 1t, 2t, 3t, then at the moment 4t in these flip-flops, this remainder must be calculated. So how this schematic operates? Basically, this performs cyclic shifting. So we have this 1 at the input of our encoding device. It's here, right? So it goes at the output at once without changing, because here we have 0 connected, right? So 1 plus 0 is 1, and is fed to the dividing schematic here. Previously, our older values of the flip-flop was zeros. So these zeros are shifted out, and this 1 plus this 0 equals to this 1, which comes in the feedback network to this input. So this 1 will be recorded inside this flip-flop at this tact. Also, as you can see, it is added here, and together with this 0, it will be recorded also here. There is no feedback XOR element here, so this 0 will be recorded instead right here. So we will have the values by the end of the first tact, yes, 0, 1, and 1. Then the next time interval, another code word symbol comes, 0, which is directly output, and we can see here that we already have output 2 symbols, right? And is coming through this feedback network as sum here. Our previous values here, which we have calculated at the time 1t, were 1, 1, 0, right? So this 0 comes here, this 1 will come here. In the feedback network we have 0, so basically this 1 will come here, and this 0 will come here. So we see here that we are performing shifting, and for the middle flip-flop, yes, we are putting inside not just the value of this flip-flop previous, but the sum of this flip-flop plus input data plus this. So what is being recorded inside here is Z0 plus, that is responding to this input data, plus Z1 and Z1 corresponding to this. And this is the third trigger, which is Z3. So basically that is our generator polynomial, right? If we write this Z0 as 1. That's the logic of the schematic. So this process is continued, and I will maybe not burden you with formal details. I'll just show you what happens, right? And if you are interested, I will provide this PDF file in the Ortus, so you can see it and check for yourself, maybe spending some time, how exactly those numbers here are circulating. So at the third time interval, we had previously values like 1, like here, right? What we have recorded in this second time moment, those were our old values. At the input we have 0, and 0 together with this 1 gives us 1 at the feedback network, which is recorded here, and here as well, right? Here we had 1, which is recorded here. So basically, by the end of this tact, we'll have 1s in each of the flip-flops. And the next tact is the time when we must have calculated the remainder. So what happens is we get last information symbol, 1, right? Which together with this previous value 1 would give us 0 in the feedback network. That 0 would record here, and together with this XOR, it would record here as 1, and this one would record here as this previous value. So I'm doing that quite fast and brief, but what matters the most is that actually by the end of the fourth tact, we are going to have our remainder here. Please note, however, that everything is in mirror here. So our output data, our code word is mirrored, and the remainder is also mirrored. So basically, this is our remainder, and the next symbol that will come at the output will be this one at the time moment 5, at the time moment 6, this one, and the time moment 7, this one, which matches this correct order, right? So we have calculated this remainder, and now what we must do is to add it at the end of this data. How are we going to do that? For that, in the time moment between 4t and 5t, we are going to switch this connection, right? Therefore, the data will come this way. At the same time, remember that we have added zeros to our data, so this will be 0. And this way we would add our remainder at the end of the data. So at the time interval 5, the first one was this one, went here. At the time, well, and basically what was here has come here, right? And at the time moment 6, this will be appended, and this was here. Here we have 0, right? So basically this XOR never changes anything because it adds up 0 and nothing is changed. At the same time, these triggers are nullified, making them ready to work with the next data block. So what happened at the 7 time interval is that we have obtained our code work, only it's in mirrored code word compared to this, right? So it's 1 0 0 1 1 1 0. And our triggers are once again at the 0 state, meaning that we can start sending the next data, right? And continue this process uninterrupted. So it takes 7 time intervals to get the code word. That's how encoding device works. So as you can see, the logic is much more difficult, but still, if you know the algorithm for multiplication in computer processors, it's very similar, shifting and adding, shifting and adding. So let's talk about decoder schematic. Decoder schematic, however, will be much more complicated than for group codes. However, also much more compact as well. The basic operation also will be division. However, now we need to divide considering all the M symbols received, including control symbols. Also, the schematic is made of shifting register and XOR elements. So in general, it looks like this. Please note that previously we had XOR element here, which was making that feedback, and input here. Now we have moved it over here at the input. That is the very same element which has been moved away, right? And for the rest part, it's made up the same way as before. So for our generator polynomial, we still have XOR element after the first flip-flop. We don't have after the second flip-flop, but this XOR, which was last here, now is located at the beginning. So accordingly, if we are going to make modifications here, let me make that at once. We no longer need any switch as well. And I'm going to remove that irrelevant part of schematic and put XOR element here. So our feedback now to make it shorter, like this, here, and here, right? And this is our input. So this is schematic of division by M time intervals. So that's what's basically changed. Literally, we moved that XOR element from the output to the input, and nothing really changed. Also, please remember that this schematic is drawn for the generator polynomial z third plus z squared plus 1, not the same polynomial as in example, right? In example, it was without the second power here, and therefore that XOR was located here. So that is only schematic required to perform division and find the remainder. This, however, is far from the entire detection device, because we need to have some way of correcting that error, right? First, locating, which is not quite simple, as you have probably already mentioned and noticed from this table of the syndromes, right? Where that table was here. There is no logical order in these syndromes, right? So we will need some way to find that order, because actually there is a property in these syndromes. For example, I can easily obtain this syndrome if I know this one. For example, 1, 1, 0. I append an extra 0 at the end and add generator polynomial, which in my case is this one, plus, and I have gotten this next remainder. Even more so, if I append 0 to this one and continue adding, I'll get the next one. And I can continue that as long as I want. Because I have started over with the first syndrome. Right? And basically, if you look closely, this actually very remains the division procedure, right? So you can actually calculate those syndromes by simply converting them from one to another. How we can do that further, right? For example, here, after I put an extra 0 at the end, I really can't add 4 numbers to this, right? I need to have 1 at the beginning in order to be able to add something to it. So I'm not doing anything and just taking last 3 digits as the remainder. Append next 0, last 3 digits as a remainder. Append next 0, and then I can add, right? And I would get, surprisingly, this remainder. Append 0, last 3 digits as a remainder, right? So basically, even if you have M31, don't be alarmed, you will not have to divide 31 times these 31 symbols, right? You can easily get those syndromes one from another. And also we will make a program to do that. So for decoding device, right? This is for our case of generator polynomial Z3, Z plus 1. This was for the generator polynomial Z3 plus Z2 plus 1. And now we need to improve this. We need to find where the error has happened, and we need to perform correction. For that, we are going to use the Megit algorithm, which can be used to create 2 types of the schematics. First is only to detect error, which will not correct it. It's, of course, simpler way, but why would we want to do that if we can make with an extra work, right, correction of that error, which is, of course, more desirable. But anyway, let's see first this detection option, since it will be the base for the correction. As you imagine, in order to be able to correct error, you first must be able to detect it, right? So basically, this will be just an extra step to correct that error to this diagram. So what we are seeing here is the simplified structure of this decoding device. And the heart of this decoding device is this M-tact dividing shift register, which was shown here, right? So basically this has input and we can output from the triggers the result. And error detector is very simple. What it does, it checks that after the 7 time intervals, no, M time intervals in general, whether the contents of these triggers is 0. If it is, then there are no errors. If, however, any of those triggers has 1 inside, then that is the error. So that's how detector works. It's simple OR function, right? So basically that would be OR, and we need to connect each of these outputs. So if any of those triggers inside has 1, then output will be 1, which will be the signal for error. If all triggers have zeros, then output will be 0, meaning that it's okay, no errors. What is this buffer register and why do we need? Actually, this is the memory. A memory of total of 7 time intervals, which is needed to wait for the data while we check it for errors. So idea is very simple. We need some way to delay the information before we give it any further, right? So here, for example, is a processor which expects data. We are not quite ready to tell this processor what we have received unless we have checked that for errors. So we need to delay data for the time while we check for errors. If anything is okay, and error signal is 0, this data will be given to the processor. If, however, there will be error, the processor will not process this data in vain. It will be notified that there is an error, and it will not even bother with this data and request to repeat this data block, right? So that's the idea why we need this buffer register, so that we don't send the data with errors further. If we are drawing this schematic more detailed, then we have here this division schematic, right, which calculates the remainder. Then we have this OR element, which checks if the remainder is 0, right? And its output signal is connected to the reset port of the triggers. Here is the reset input. So if we send 0 there, then contents will be erased and data will be discarded, right? So in order for that, we need not simple OR function, but OR with inversion here. So basically, we need some OR, that general logic, and let's see if we have more inputs, 5 inputs, right? 4 inputs. And okay, so we don't have 4 inputs simple nor. Let's see what we don't have also reset. Let's see our buffer register. We need some, well, maybe shift register it's called. No, not shift. Well, at any rate, I will check that during our break, maybe how we can draw particularly this part, right? We can, of course, always put the number of required flip-flops simply by copying them But if you have M equal to 31, then that would mean that you would have 31 of those flip-flops here, and there are universal registers, maybe it's called like this. The universal. Well, anyway, I will find that required element, which will be with a single block, right? Single block, which will perform required delay for us. So we'll return to that at the example part. But for now, the idea is quite simple, right? We calculate remainder. If that remainder is 0, then data is not reset and is given further. However, we cannot with this schematic perform any corrections. We need to go further. For that part, we need to improve our structure by adding the second dividing schematic, which will continue division of the remainders. Actually, what happens is that it will continue to get the next and the next remainder until the last one has been received. So when we will receive this, then it's time to stop and correct the error right now. I will show you how that logic works when I will describe an example. So that's why we need the second schematic, because the first schematic will be busy with processing the next code word that comes after our code. You must realize that this is an uninterrupted process. So we have received code word, this schematic calculated the remainder, given the result to this, and it's already time to start processing the next code word by this schematic. So while this schematic processes the next code word, this finishes work and tells the error detection when do we need to perform correction. So you can see here the element that actually performs that correction. So let's see how that works. First of all, we need to make the error detector. If in this case the error detector was just a simple OR function and we needed to check whether any of these is actually 0 or 1, then for this case error detector must be set to find specifically only this syndrome, and any other syndrome should give 0. So we are talking about synthesis of logical function with such truth table that syndrome is 0, output is 0, syndrome is 1, output is 0, syndrome is 2, output 0, syndrome 3, output 0, and so on. And I think perhaps I have a little bit misplaced these two values, right? And sorry, it's actually not a table of the syndromes. It's not this table. It's just they are just typed in the possible combinations of these syndrome values. And we need a logical function that would give output 1 only in this case. For any other case, the output should be 0. So it's quite simple to make. We only need to use AND function, right? As you know, AND function gives output 1 only in one case, if all the inputs have 1. These two are already 1s, and this one is 0, which must be inverted. So in this way, only this combination would trigger output of 1. Any other type, for example, if we have 0 here, then 0 will go here and output is 0. If we have 1 here, 1 will go here, output is, after inversion, that would be 0 and output 0, right? So only this way we can actually do that. And even more so, we have this inverter included in our flip-flop outputs, right? So you can see here that we have direct output and inverted output. So If the flip-flop contains 0, we are going to use inverted output. If the flip-flop contains 1, we are going to use direct output, right? And here we are going to use AND function as the error correction signal, which will be added by XOR to the data. So let's see how this schematic looks in details. Here you have two division schematics, right? This one, literally the same, which are connected through these switches, switch 1, switch 2, and switch 3. Yes, and switches connect that. So this one, output of the first schematic, third trigger, connects it to the input of the third trigger in the second schematic, right? So third gives information to third, second gives information to second, and the first gives information to the first, right? So they are connected through these switches, and the switch is activated in the time interval, not 7, but not 40, but from 7 to 8, when we have calculated the remainder. And the remainder must be calculated within 7 time intervals here, right? After that, we must pass the information to the next schematic, and at the time interval 8, already the new data will start coming here. Then we have error detector here, which is AND schematic, right? And as I have told, for the syndrome of 1, 0, 1, which is set to this error correction schematic, we must output direct outputs where we have 1, that would be here and here, and inverse output where we have zeros, that would be here. And then this is put here when we correct. Note that I have put here that universal register, which is basically the same thing as the series of the 8 of those individual flip-flops. So I will try and find what element in this tiny cat can be used for this purpose. So how does this schematic work? Let's see example for the code word, which we have described here. This one, right? So that would be 0, 0, 0, 1, 1, oh, 0, 0, 1, right? And we have an error in this position. So how does this schematic work? And also I will write what remainder we have found. So remainder will be 1, 1, 1. That has been calculated here. So let's see how this schematic will work. So first of all, it will take 7 time intervals to record that data to this register and perform division in this diagram. So it will take 7 tacts, right? After the 7th tact, here inside those triggers, we will have the remainder 1, 1, 1. In between the 7th and 8th tact, it will be copied to these triggers, which is not the last syndrome from this table. So this error detector will produce 0, right? Because it's not matching the remainder it has been set to track. So what happens at the time interval 8 is that the first symbol of the data comes both in this register, forcing to leave the first symbol of our previous code word, that would be 1, and start dividing procedure here. At the same time, this schematic will continue a division and will advance from this to this, right? So basically, then at the time interval 8, we will have the remainder 1, 0, 1 here, which is not yet read, but stored inside, and will be read at the time interval 9. Next, at the time interval 9, what happens? At the time interval 9, the next data symbol is being read, which turns out to be this 0 here, right? And this data is output. Sorry, not here. Producing 1, which comes all the way here, inverts that 0, and outputs it as 1. As you can see, that is the exactly right moment when we had to correct that error. Then this same 1, sorry, 1 will be sent at the input here and nullify this register. So basically afterwards here we will have zeros all the time, and no more correction will be performed after this moment. So what will happen at the time moment 9 will be that we get next symbol, at the time moment 10 this symbol, 11 this symbol, 12 this symbol, and 13 this symbol. Or 14, that would be right. I have already missed somewhere something, right? But the idea was that the correction has been performed exactly at this time moment. Now, if we would have error, for example, in the very last symbol, then at the 7th time interval, there was a copying of the data here, and we had this remainder. And consequently, it would take 6 time intervals to go from this remainder to this remainder, during which these symbols will be output at the code output, right? And at the 14th time interval, it will be returned to output. I'm sorry. Symbols will be output from 1 to 6, these symbols, right? And the calculated remainder in this diagram would be this one. And when it will come time to output this symbol, then there will be a signal that we need to perform a correction of error. And effectively, this error will be corrected. So as I have told, the logic for this is much more convoluted, but the schematic itself is much smaller than schematic of this device, right? So yes, that's both good thing and bad thing at the same time, but well, you will have, if you have cyclic code, to create this schematic. So now we can make an extra break of 10 minutes. Yes, and then I will show you how to calculate the example. Basically, I have already shown, but let's spend some more minutes, like 20 more minutes, for your course project part as well. So see you again in 10 minutes at 15:50, right? And then we will conclude our today's lecture. So thank you for now, and see you again in 10 minutes.